I will import numpy as MP and MATLAB and matplotlib. So we can see what principal components are, and then we can visualize them. Now, what I'm going to show you is a matrix. That is 2 by 6. So it has 2 columns and six rows. This is a very simple matrix, and it's just it's small enough so that we can get the point of PCA. And then, of course, in the next example, we will look at a large data set. So this one only has 2 dimensions. Ultimately, what we want to do is we want to project this 2-dimensional data onto into one dimension. So we want to go from essentially 2 vectors to 1 vector. Let me explain what I mean. So we are going to perform SVD on this. Okay, and remember we said that PC is a special case of SVD. Now, we're not going to do this. We're not going to use Graham Schmidt and normalization. We're just going to use a built-in method of NumPy called SVD. So there's a method called NP SVD in the object linear algebra. And its return value will be 3 things. And it will be 2 matrices and 1 vector, which you will assign to U, S, and V. So the return value of this method will be a matrix, vector, matrix, respectively. And this is SVD decomposition. And then I'll print all 3 variables. So I'll print U and S and V. So this is the matrix U. The eigenvalues that will be put in the matrix SS for sigma. Okay. In a PCA, the S is a sigma. Use the Greek letter. And the matrix V. All right. The next thing we are going to do is I'm going to put these eigenvalues in an identity matrix. So again, you see here, this is an identity matrix. But instead of ones, we have the eigenvalue. So I'm going to produce this square matrix. And to do this, first, I will assign lowercase s to uppercase s, because the convention, we want to follow linear algebra convention where we use lowercase letters to denote vectors, uppercase letters to denote matrices. So I'm going to change uppercase s to small s. Uppercase s instead will be a matrix. If you see, this is in echelon form. We have ones across the principal diagonal. We need this to be a 6 by 2 because of the matrix operation that we're about to perform. But this is the first eigenvalue, second value, or if you like, the first singular value and the second singular value. Also, if you like, the first principal component and the second principal component. Once I start visualizing, you will see how we're able to reduce the dimensionality of our data. Now, imagine this were an Excel sheet. We have 2 columns of data. What we're about to do in this example is collapse it into 1 column. So we go from a 2-dimensional data to 1-dimensional data. That's the linear transformation, to go from R2 to R1. Now, I also want to do this. I want to plot this vector on its own axis, plot this on its own axis. So this will be, let's say, x, and this will be y. So here we will say performing SVD, principal component, SVD. First, we need to decompose the matrix into 3 matrices. Then we are going to visualize the column vectors of A, just so we can have a intuitive understanding. Now, I'm going to use a technique called the list comprehension. So if you haven't seen this before or you don't remember it, let me show you. I'm going to go A, that's the matrix, and I'm going to use a square bracket. Of course, if you plug in a number, and these are the indices, every index will correspond to a particular row of a matrix. So if I type in 0, this will be the first row of the original matrix. And of course, we remember that we count from 0 in programming. If I want the last row, I go 5. Now, if I want all of the rows, what this colon means is that what precedes the colon is the starting range, and what comes after is this ending range. So if I type this, if I leave both sides of the colon empty, that means give me all of the rows. So here we can see the first row is -3, -3. The second row is -2, -1. So if I just want the first 2 rows, I can go 0, 1. Or rather 0, 2. It has to be the stopping index. There we go. Now, what I actually want is all of the rows, but I want to only extract the first column. So I'm going to call this C1, and it will be -3, -2, 1, -1, 2, 3. So what I'm going to say is I want all of the rows from the first column. And that will give me these components. And I'll also do it for the second column. So all of the rows from the second column. Again, we count from 0, which is why this is 1. Now I will plot these 2 vectors. So C1 and C2 are both now vectors. Okay. However, I'm going to treat these as points on the x-axis. And for C2, it will be points on the y-axis. Basically, we will just draw 2, one horizontal and one vertical column. And I'll say why, and I'll show you why we want to do this. So to plot, I'm going to use the PLT method. PLT dot scatter. So I want C1 to be on the x-axis. So I'm going to type in C1. For the y-axis, I'm going to set it to 0. Okay. 6 elements corresponding with the 6 points in that vector. And then, I should have all see it as PLT here as well. Yeah, thank you, Ron. I fixed that. Now, I also want to color code these points. So this will be 0, -3, excuse me, -3, 0, -2, 0, 1, 0. See, there's points, right? These are the points corresponding to the x-axis. These are the points corresponding on the y-axis. I want to color code these. I want to color code the x points that are to the left of the origin. Basically, the numbers that are negative will have one color. The numbers that are positive will have another color. So I'm going to say C. C is the parameter for color. And the criteria for choosing the color is C1 greater than 0. So if the components in C1 are above 0, we will get one color. If they are below 0, we will get another color. And let me just set no, never mind. It's going to change dimensions. Let me just see what this looks like. Okay, there we go. And I will do the same for the second column of matrix A. Maybe what I should have done is typed in make this A1, A2. Make it clear. Let me run this again. And then A2. Let's change the order of these arguments. So the idea is this. We have two dimensions of data, these two vectors. And what we want to do is retain this spread, this variation, but in one axis, in one vector. So I want to retain this value, this spread, in one diagonal. So here, this is one dimension of our data, the second dimension of our data. And what we want to do is use the principal components, which are the eigenvalues, to collapse these into one axis while keeping this spread as much as possible. So here's what I'll do next. I am going to take the first principal component multiplied by the first principal direction. Let me open this again. Now I know it's quite maybe messy, but the first column vector in U is the first principal direction. What I'm going to do is I'm going to multiply the first principal component by the principal direction of the matrix U. Now, the principal component is also the first principal component is the component that has the largest value. So if I come back here, if we look at this example, this was a completely different matrix. The largest singular value or the largest eigenvalue in this matrix is the number 14. This number also corresponds in the context of PCA to the variance in the data. So the first eigenvalue is the first principal component, and it's also it represents the largest variance in the data. Now, in order to understand why we need to keep the variance of the data, we'll have to look at a second example. So first, we will focus on visualizing and understanding dimensionality reduction. And then later on, we will look at another example where we have a larger data set and a covariance matrix is involved. This example, since it's only 2 columns, is too small. Okay. So let's see the principle, let's see the dimensionality reduction first, and then we will talk about covariance and correlation matrices. Okay. In order to visualize our first principal component, we will take S, if you remember, S was the, okay, why did I not run the cell? Let me run the cell again. No, I have to run it from the top. Oh no. Yeah, so S is the eigenvector. And this is the largest principal component, which will be the first principal component. So in order to get the first principal component, we will use index 0. We will then multiply this by the first column of the matrix U. So again, if we return to here, to this writing, if this is the matrix U, we're going to multiply this principal component by the first principal direction. So I'm going to multiply this by U. I want all of the rows from the first column. If I run this, I now have a linear transformation. We've gone from matrix to vector. So this is the vector corresponding to the first principal component. If I plot this now, if I go PLT, I have to code here, by the way. Plot principal component one. So I'm going to pass this twice, and let's just call this PC1 for, by the way. PC1. So the points on the both X and Y axis will be PC1. It's a line that will go through the origin, and it will be linear. Where PC1, the components in PC1 are greater than 0. I'm setting the X and Y limits to -5 to 5 for both the X and Y axis because, well, the components of the principal components grow from -4 to +4. So we just want to make room to so we can see it. This is the result of PCA. We have taken those two dimensions, which you can see were quite spread. And we have combined both dimensions. We have combined both vectors into one vector while keeping the variance, while retaining a significant amount of the data. If we do the same thing for the second principal component, you will see that it retains data, but not as much as the first one. This is amazing because if there was any correlation, if there's any significant relationship between the two first columns, well, now they are, let's say, merged or combined into one dimension. So we've gone from 2 dimensions to 1 dimension. This will become incredibly powerful, especially when we have large data sets. We go, for example, from 20 dimensions or 15 dimensions down to 1 or 2 or 3 principal components, making the job of the machine learning model a lot easier. Now, there's more to our discussion. So we haven't even gotten into the discussion of the covariance matrix yet. But we'll do that. Let's actually leave this here for later reference. Hopefully, you've understood what we mean by dimensionality reduction.